Assalamualaikum warahmatullahi wabarakatuh. My name is Kuratun Ain binti Misbah, metric number 1622818, and this is going to be my FYP1 video presentation. So my title is The Investigation of Control Methods in Parrot Mini Drone to Monitor IIUM River, and I am supervised by Dr. Muhammad Kasha. Alright, so in general, unmanned aerial vehicles, also commonly known as UAVs, they are extensively used in many field of applications, ranging from military, civilians, as well as commercial activities. So for example, many UAVs are used in surveillance and product deliveries, as well as agricultural activities. So in this project, a quadcopter, specifically a Parrot mini drone, is going to be adapted to be used to monitor the IIUM River to detect physical pollution. So for most UAV applications, the control method that is adapted into it is the PID controller, which is the proportional, integral, and derivative controller, because of its simplicity. However, this controller is not robust, and there are other types of controller, but for most of them, these controllers, they work well in simulations, but then they don't give the same results in real practice. So in this project, we are going to develop a control method that is robust enough to be used to monitor the IIUM River.
Figure 1 shows the Parrot Mambo mini drone that is going to be used in this project. This quadcopter has a built-in initial measurement unit, which consists of 3-axis accelerometer and 3-axis gyroscope in order to evaluate the speed, tilt, and obstacle contact. It has an ultrasound sensor as well as pressure sensor for vertical stabilization.
Control performance is an important criteria in implementing quadcopters to monitor IIUM River. However, there are a few concerns when you want to implement the control method in real time. So these problems are the main drive to actually develop a proper control method that is suitable for the application of this project.
First, the current control technique that is widely used in quadcopters, such as PID controllers, are not robust enough for this application. On top of that, PID only works for a single operating condition, whereas we would like a controller that works for multiple operating conditions, since a quadcopter is a complex dynamic system. A quadcopter is a non-linear system that has its degree of freedoms, which means it has 12 states, and with a control system at most we could only control 4 states. In addition to that, there is also the issue of power balance. Since the quadcopter will be used outdoors, the power consumption should be optimized. With a high performance of control systems, there will arise the issue of high power consumption. Consequently, the quadcopter might not be suitable to be used for an extended period of time, which we would like to avoid. Therefore, there should be a balance between the power consumption and the performance trajectory of the quadcopter.
So the main purpose of this final year project is to select the proper control method to be implemented on Parrot mini drone in order to be used as a monitoring device to detect pollution in IIUM River. So in order to achieve this main goal, there are a few objectives that need to be predefined.
The first objective is to study and compare different control methodologies for quadcopters. This is to benchmark several control methods so that the best control method for Parrot Mambo can be selected. The next objective is to optimize the performance of the selected controller. Once the proper control method is selected, the performance of this controller should be optimized to give the best flying condition for the quadcopter. The Parrot Mambo mini drone should be able to adapt to uncertain conditions, and most importantly, there should be a give and take between the power consumption and the performance of the system. The last objective is to implement the controller both by simulation and in real-time experiment to see if the selected control method will be successful.
There are many studies that have been carried out about control methods on quadcopters, and in this video presentation, I will highlight a few of these research studies.
The first paper is on the altitude and position control of Parrot Mambo mini drone using a PIPD and FPIPD controllers. Shown here is the equation of motions for the nonlinear model of the system. The first equation is the translational equation of motion, in which B is the thrust coefficient and gamma is the angular velocity of the rotors. The angle phi, theta, and psi are the roll, pitch, and yaw motion of the mini drone respectively. In the second equation, tau is the thrust from the rotor, L is the distance between the center of mass of the mini drone and the rotors, and D is the drag of the rotors. The authors then linearize the model by using the hovering condition as an operating point. The resultant linear equation of translational motions for each direction is as shown. The parrot mini drone that was used in this research paper has a built-in PD controller, which is proportional derivative controller. In this study, PIPD controller is integrated on the system, and the block diagram is as shown in figure 2. So the authors first designed an outer loop of proportional integral controller, followed by the inner loop of proportional derivative controller. The authors then apply the controller experimentally, and the results are as shown. Based on the results for the altitude control, it can be seen that the built-in parrot PD controller is not stable and has significant steady-state error. When the PIPD controller is applied, the steady-state error is eliminated. In addition to that, the settling time is also enhanced without any overshoot. For the precision control, as the PIPD is applied on the parrot, the settling time is reduced and there is no overshoot. However, steady-state error is still present. Therefore, the system is definitely improved, but the errors are not eliminated. Hence, it can be said that the system is not entirely stable yet. The next paper is on PID, which is the Proportional Integral Derivative Controller, LQR, Linear Quadratic Regulator, and LQR PID on a quadcopter platform. In this paper, the performance of PID controller and LQR controller is compared. Here, the vertical attitude equation is shown in state space representation. In the equation, Z represents the vertical coordinate in Earth fixed frame, W is the vertical speed in body fixed frame, and omega is the angular rate of each propeller. Figure 5 and Figure 6 shows the position step response for both LQR and PID controllers. It can be seen that LQR performs better than PID as it has no overshoot. PID shows a faster response time, but that does not mean that with disturbances present, it will show consistent results since these controllers are not analyzed for robustness. For the vertical speed response, the speed response with LQR control is null after a transition time because of the regulated controller, but in real time, due to the disturbance present, the vertical speed does not necessarily go to 0. Next article is on parrot UAV controlled by PID controllers. In this paper, PID altitude controller is designed to stabilize the vertical position and is simulated. It must be noted that during the simulation, the changes in pitch, roll, and yaw angles are assumed 0, hence the PID only controls signals that cause the parrot UAV to hover or fall in a vertical direction. Based on the result, it is seen that for the range time of 0 to 20 seconds, the simulation does not achieve the desired value of 0.8 meter.
Moving on to the methodology of this project, there are several processes that needed to be completed in order to achieve the objectives of this project.
These processes or procedures are shown here. First, it is very important to learn about the different types of control available, just to get the basic of it, to see what works and what doesn't, and followed by learning how to model a dynamic system on MATLAB Simulink, as this is the software that is going to be used to simulate the performance of the controller. Then, an LQR control can be modeled for parrot Mambo mini drone. So LQR control is chosen because it is a robust control and it makes the quadcopters adaptable with disturbances with minimum error, which is unlike PID. And then the control method should be applied experimentally to finally obtain the results and see if the control method works consistently in simulation and in real time. The Gantt chart for this project is shown here. This is to ensure that this project is completed within the 14-week time period, which is 1 semester. And these are some of the references used during the research period of this project.
That would be all from me. Thank you.